Let's start out talking big picture about this project. So the idea here is to measure an exoplanet transit, and as a reminder how that kind of thing works, here's a animation of a transit. So what's happening in this situation is that the exoplanet passes between us and the star it orbits, and when it passes between the two of us, the brightness from the star dips just a little bit. Size of the dip here is typically about 1% of the star's light gets blocked. And so it's not a big amount, but it's an amount that we can often measure. Whether we can measure it depends on a little bit on how bright the star is and what the seeing conditions and other atmospheric conditions are. So as a couple of examples of this, here's the first exoplanet transit that was measured at MSUM. And the feature to point out here is this lower part where the light from the star dipped down. So we caught just a little bit of the beginning of this transit, then the dip, and then some light after the transit had ended. And the transit's the part where the star or planet passes in front of the star. I'm going to skip a couple. Well, actually, no. Let's talk about this. So we're doing the exoplanets you're looking at were identified by the TESS mission, and you might ask, why does the TESS mission need us? This is a typical view of the what the TESS mission would see through its cameras. It's deliberately a low-resolution camera, or at least a low-resolution view of the sky, so that it can see a lot of the sky. And a similar view from the a ground-based telescope would look much more like this. You can see much more detail. And what we're trying to do for TESS is nail down, if TESS sees a dip, when does that dip happen, how deep is the dip, and which star is the dip occurring on. And all of those points marked in green are points that could be the place where the dip is actually happening, rather than the star that's at the very center there. And our role in this is to see when those dips happen, how deep they are they the same size dip in a couple different colors of filters, to nail down really well, is this possibly an exoplanet transit? And if it is, when does it happen and which star does it happen to? So that big observatories in Hawaii can do additional observational work on these stars, measuring their spectra to measure things like the surface gravity and the temperature that you need for your exoplanet fitting, and do adaptive optics imaging, where if this candidate that we're looking at actually turns out to be two stars, it can resolve those two stars separately, and do what's called radial velocity measurements, where you measure the motion of the star that's caused by the planet, and that last piece is really where the planet conformation happens. But those observatories in Hawaii cost a lot to operate. There's very limited time on them, and so they don't want to go pointing their telescope somewhere hoping that they might see something. They want to know for sure that they are going to see something when they look. And as an example of the kind of thing y'all are doing in class this week, or the last few weeks, you had a test candidate, and TESS wanted us to look at the star in the center of that field of view, and all of the green marked stars. Also look at those to see if maybe the dip is really happening in those stars. And the graph that you get out of this kind of thing looks like a graph that you are looking at this week, where there's a dip caused by the exoplanet transit. In this particular case on the screen, you can see a little bit out of transit before the transit happened, then the dip where the transit happens, and then some time out of the transit. In some of the ones that you're looking at, you might only see the first half or the second half of the transit. So with that background, let's review some of the steps that you've done. So you started out with basically an empty exoplanet folder, and whoops, I need to go back in here. I'm just going to grab the name of this one. So first thing I had you do was look up some information about that exoplanet candidate. Let's close this up. So you ran this notebook, and the purpose of this was to, for a particular candidate exoplanet, look up some information about the transit. So this has an estimate of the depth, the error in the depth, the duration, the error in the duration, the epoch, which is the time at which the transit is supposed to occur, the error in that, the period, and so on. The other file that was generated here with a name that looks something like this, we'll come back to in a moment. So once we had this information, I wanted you to do some photometry, and the idea of photometry is to measure the light from a star. In software, you draw a circle around the star, add up all the light inside the circle, and then subtract the sky background near that circle, the average background. As a prep for that, the next step you did was to enter some information about our camera in our observatory. And after you'd filled this out, the camera information looked like this. This had some information like the gain and the read noise that's needed to calculate some of the errors in our photometry, some information about our observatory, and about our filters or passbands that we used. Next up, you measured a couple of the things you need to measure to be able to generate the list of stars that we're going to do photometry on, and to measure the size of a star so that when you do that photometry, the software knows how big a circle to draw around each star. And I'm going to start out in this tab. The first step when we're doing these exoplanets is to read in this list of sources that the test project has said the real event could either be in the exoplanet or any one of these sources, and so they want us to measure the light from all of those sources. I need to get back to calibrated nights, and I think that this was taken on October 8th. Yep, so I'm just going to grab one of those. This takes a moment to load. But then once it's loaded, at the center here, we've got the exoplanet itself, or the exoplanet candidate itself is here at the center. And then all of these places where you see green circles around that are stars that are close enough to that the variation that TESS thinks is coming from the center star could really be coming from this nearby bright star or that nearby bright star, or maybe it's a really deep event in one of these super faint stars that we can hardly see. And at this stage, there were a couple things you saved. You saved some information about variables. We're not going to end up using that this semester. But behind the scenes, that also wrote out in source locations.ecsv the location of all of the circled or marked stars in this field of view. So the green ones are ones that we want to measure the light of. The red ones are stars that are going to be used for comparison. So in a couple of minutes, when I talk about eliminating atmospheric effects, those are the stars I'm talking about. And the ones marked in blue are variable stars. So to get the size of the stars, what you did over here was you zoomed in on the image, you did a shift click, and you got a few plots. So this first plot shows the highest signal to noise ratio that you get. And it's important because the percent error in your measurements is going to be roughly 1 over the signal to noise ratio. So if I round that down, signal to noise ratio here is 140. If I round that down to 100, do 1 over 100, I get a 1% error. And the red line is the suggestion from the software of where to put the circle around the star. So you don't want it right at this maximum signal to noise place because the size of the star can change a little bit over the course of the night as the atmosphere changes or conditions change. You also get a plot like this that shows the full width half max and the size of the aperture. So here, and if you look at this, you can see that we're making the aperture big enough that we've got all of the light from the star plus a touch extra. And the portion of the image that we'll use for getting that sky background is in the second group here. So both these settings, you had to click the save button down here to save. And so as a reminder, what we've done here is we've identified each of the stars we would like the software to measure the brightness of, and what size circle to use when it's doing that brightness measurement. Although technically when you run this next notebook, all of the settings have already been saved. It's not a bad idea to take one pass look. So I'm going to check here the photometry apertures that we just set. Over here look like they're the right numbers, 17.5 and 15 looks good. This source locations file is the one that we wanted. There were a couple of options you changed here, so I don't want to go into the details of why you had to do this, but there are a couple settings to change. Oh, and it's reminding me that I need to change those settings, so I've done that. And a couple other things here you didn't need to change. So once all that was done, we're ready to ask the computer to perform the photometry. So in other words, go through every image, and for every image, go to each of those star locations that we set. Draw a circle around the star of the size that we just decided on, and write out a essentially big Excel spreadsheet at the end. It's not saved the same way an Excel spreadsheet is, but make a big Excel spreadsheet at the end with all of the stars, or the brightness information for all of the stars. So I've got to go back to calibrated nights and the particular night of data here, and select one of these images of that object. Yep, that's correct. And so in the background, this has started running a photometry notebook that's using the computer to loop over all of the images from that night, and for roughly 500 or so stars in each of the images, put a circle around the image of the size that we asked for, and then make a table of those results. Okay, I paused the video for a little bit while I was doing the photometry because it's just not that exciting to watch. Right, so now we're to the point where we have some photometry data saved. It's in a great big huge table, which is not very readable for a human. Actually, I'm mildly curious how many rows does this have. I'm going to guesstimate around 20,000. So our next step in this process was to try to take out atmospheric effects. So if you remember from a few weeks ago, we talked about the effects of the atmosphere, so stuff that's not smoke, our telescope, its filters, the camera itself. All of those respond to light in different ways. In the case of the atmosphere and smoke, the way that or the fraction of the light that gets through the atmosphere depends on which night you observe and can change during the course of the night. And the way that we wrote this down was that this FT on the far left was what you get out of the camera when you do the photometry that we just did. The FL was what the value amount of light was above the atmosphere. And then all of these little Fs were the fraction of light taken out by the atmosphere, or that gets through the atmosphere, the fraction of light that gets through the smoke, the fraction that gets through the telescope, and so on. So each of those little Fs reduces the amount of light that gets to our camera. And one way of removing the atmospheric effects was to look at the ratio of light of two stars, because if you take a ratio like this, all of the atmospheric and telescope effects cancel out if the stars are all the same color. And so what you measure as the ratio in your telescope is the same as what you measure as the ratio, or the same as the ratio of the light above the atmosphere. In our case, the star that we compared to was not actually a single star. Instead, what was used as the comparison star is the light from every single one of those little red dots. So the software found the light from each of those stars with a red triangle around it, added up all of that light, and that's what was used for calculating this flux ratio in the denominator. So it was the FT1 down here. And then for each of the green dots and each of the blue dots, this differential photometry, which is the fancy word for taking the ratio of the flux, was done to come up with what we call a relative flux, relative because we're taking the ratio. So that's not calculated during the photometry. We had to run another notebook for that. The calculate relative flux notebook. And there we had to pick our photometry file and our source locations. And then you click the Add Flux column button and you wait a little bit. And once we are done, we've got a new file out here called photometry relative flux. And what that's done is add several new columns to the spreadsheet. And those new columns are the counts from whichever of those green stars you're interested in, divided by the count from all of the red stars put together. And I should say that the flux, so in other words, the flux from those green target stars or the flux from a particular red star is the number that you get when you add up all of the counts inside of the circle. So the stuff, I know it seems kind of disjointed because we did it over several weeks, but it all does connect back together when we're doing these measurements. Okay, so next up, what do we do next? We took a quick look at your data, and I think this was probably the Monday before Thanksgiving that we did this. So we selected the relative flux, and then the test info file, and you may have had to select a filter. This cell may give an error, that's fine. It just means that in this particular case, there was no problem. And this is where we get to the prediction part. So let me rewind a touch. Looks like I closed that. Let me reopen it. So the information that's stored in this test info file lets you predict when the transit should be. So the point of doing these measurements is we have a prediction from tests of when a transit will happen, how deep it will be, how long it will last. And we're doing observations to confirm that that really is when a transit happens, that it really lasts as long as they think, that it's as deep as I think it is, that it has the right properties to be an exoplanet transit. In this particular case, I get a graph that looks terrible compared to your data. So my mistake here was I knew that there was not supposed to be, oh no, actually I didn't. I was off on which night to look at for this particular exoplanet, and so the prediction is off by half a day because of a mistake that I made. So your exoplanet data will be a little bit clearer than this. I'm going to pause this for a moment, and instead of continuing the analysis with this transit where things are not so clear, I'm going to switch to a different object that had a transit that was clearer. So give me a moment to do that. Okay, I'm back. So I'm in a different folder now, looking at a different exoplanet, and I had run, let's see if we have a picture of it saved in here. Yep. So I'd run, in this case, I had run the this initial model, and here you see marked in red, or where this dip is supposed to occur. So this is when the planet is supposed to pass between us and the star. We missed observing the first part of the transit. I don't remember if that's because it wasn't clear or if it started too soon or what was going on, but for some reason we don't have data earlier. And what we're seeing in this plot is a couple of things. The vertical scale here, the vertical axis is this relative flux. So I know I've said this a couple times, but that's the ratio of the light from the star we care about, so the exoplanet star, divided by the light from all of the comparison stars around it. And here it looks, and then the yellow line is the fit of a model to that. By which I mean we've got a mathematical model that we can build of what an exoplanet transit curve should look like. And the model fitting here does its best as it can to come up with a model for a exoplanet transit that matches the blue dots, which are our measurements, as best it can. So after we did this initial model, or initial graph rather, partially just to get an idea of were there problems in the setup. So for several folks, when your graph here came out and it didn't look quite right, we're able to go back and fix something in those photometry steps that had been missed. Our next step here was to do this fitting in a little bit more detail. So this is a notebook you ran, I think, for the first time just before Thanksgiving, and then many of you ended up redoing it last week. So I've got to pick our flex file, wait a moment, select the test file. Oops. And if I need to, select a filter, but there's only one filter there. There's some options here where we can change how this modeling is done, but for most of your transits, it works just fine not to do that. Displaying the model, and then we'll look at a graph. Okay, so you all got graphs out that look something like this. So a few things to highlight here. The blue data is each individual image that was taken, a dot that shows the brightness of our target star, the one that maybe has the exoplanet, divided by the light from all of the other comparison stars. The red dots are made up of the blue dots in a way, because to get each red dot, you average together a few of the blue dots, and that just helps reduce the noise a little bit. And then the green dots are the same as the red dots, just shifted lower so you can see them, and the green line is this model of the transit that was fit. These curves down here are showing you some information about what was going on in the image. So I think if I remember right, these brown dots show you what the comparison counts, so the light from all of those red stars added together was. The yellow, I think, is showing you the amount of background light. So on this night, that kept increasing. So maybe the moon was rising or something like that. And then the other curves are less important for what we're doing. There is quite a bit of information embedded in this plot. In particular, I want to focus in on a few things. So in the caption for this green line, it says we're doing a transit model. If we had done any detrending, and we didn't this time, so don't worry about it, or at least most of you didn't, that would have been noted up here. The RP divided by R star squared is the depth of the transit. It's expressed as decimal numbers, so in this case 0.021. If I wrote that as a percentage, it would be 2.1%. The method of model fitting we're doing here does not give you a good estimate of the error in that, which is why we're going to do another model fit in a second with exotic. A over R star is the size of the planet's orbit divided by the size of the star. So in this case, the planet's orbit is 11.3, if I round a little bit, times the size of the star. The radius of its orbit is that. TC is the time at which the center of the transit occurs. If you only measured part of a transit here, which is the case for this one, we measured maybe a little over half of the transit. You can't really measure when the center was because you didn't measure the beginning. And so for most of you, this TC number is going to be exactly the same as the number that you find in the spreadsheet with the predictions. So let me see if I can find that real quick. Okay, so this particular exoplanet was, what was its number? 23379. So let's see if that's one of the ones I have in here. Yep, 23379. Ariana, you're in luck. Okay, so this transit was predicted to happen at this particular Julian date. 2460584.628. If we look over here, that's exactly, or almost exactly, what's written down here. That's because we couldn't measure, we couldn't measure anything different. So that may or may not be different for you from the prediction. Okay, so there's one last step we did here, and the reason for doing this last step is that there's another way to do these fits using a program called Exotic, and to explain a little bit about the difference between these. The way the fit here is done is the computer asks the question, how would you draw a line to make the distance between the line and each of the points, those green points there, how would you make that the smallest? The way that Exotic works is that it makes a guess about each of the parameters that you put in, so the size of the planet, the radius of the orbit, and a couple things related to the atmospheric properties, and calculates for a model with those parameters how good is the fit. And it I think in this case probably uses a similar metric, so it's looking at the distance of the points from the line. And then it's got a very intelligent way of making more and more guesses. This ends up doing probably 10,000 different possible combinations of parameters, and uses those to get a estimate of what the best measurement of the planet parameter value is, and an estimate of the uncertainty. So let me finish loading this stuff. Okay, so this next one was a little bit of headache. So there's a bunch of information that this tool needs to be able to predict what the transit will look like. It needs the temperature of the stars, so it can estimate what the star's spectrum looks like, so that it can estimate how the depth of the dip will change as the planet moves across it. It needs the surface gravity, which is a measure essentially of whether the star is a red giant or not, and an uncertainty in those. Turns out this will run much better if you make that uncertainty about 0.1, since it doesn't seem to have been measured. And there were a couple of parameters you had to enter into here. So you had to put in the ratio of the planet to the stellar radius. And the place you got that from was here. So RP over R star squared is 0.021, so I'll take the square root of that. That's 0.145. Which is kind of big, really. I mean, the planet's 14.5% the size of the star. And for an uncertainty, we'll use about 10% of that. The ratio of the distance to stellar radius, so A over RS, is this other number I pointed out before, A over R star. So it's around that to 11.3. And again, I'll use 10% of that, so I'll just write that in as 0.11. I've got to fill in the observation date, so that was 2024, 10:08. Whoops. And the filter was SR. Exposure time was 120 seconds. So that all looks good. This saves some information to disk that will be used by this Exotic program when it runs. And so you run Exotic, and you've got to wait a little bit. It's downloading some stuff. And this is all information about the guesses that it's trying, how likely that guess was to be the right fit, and it's not telling you this for every single guess, but it's updating you periodically throughout its process. And then at the end, it's done. It's estimated a whole bunch of parameters. A couple of these are familiar. So the transit depth is RP over R star squared, just like we saw in that other graph a moment ago. We have a slightly different number from this fit than we did from the other one. That's fine. The air mass coefficients, we don't need to worry about too much. They're a measure of how the atmosphere was changing over the course of the observations. And this gives you a prediction of the, or a measurement rather, from your data of the time of the midpoint of the transit. Again, the result we're getting here is a little bit different than what we're getting in this graph. And the whole reason for doing this exotic thing is it does a better job of estimating some of these values. The reason we did this other one is that it's much faster to run and a little bit more straightforward to explain. So along with all this exotic, addition to what's on the screen rather, made a folder with some information, and the final light curve in particular is useful. So exotic agrees with what we saw in the other one, that the transit happened, that we only observed the second part of the half of the transit roughly, not the entire transit, and there's values with errors here for its estimate of when the transit happened and the size of the transit. And the idea is to compare the numbers you get out of this with the numbers in the spreadsheet. So the time of transit, yep, it's 233 is this one. Let me highlight that row. Right, the time of transit is here, so you can compare this predicted value with what we got. And if the two are the same to within this uncertainty of 0.032, then they're the same. If they're different by more than that, then they're different. The period we don't measure directly, it's in here, but you don't need to worry about it. The predicted depth is 1.89%. And what do we get from exotic? It says 1.84% plus or minus 0.0064. So as long as if those two numbers, the 1.8 and the 1.84, are within whatever this uncertainty is of each other, then what we observed is consistent with what the prediction was. For a couple of you and somebody else observed the same planet but in two different filters. One of the characteristics of exoplanet transits is they look the same through whatever filter you use, because the planet blocks the stars' blue light and green light and red light and yellow light, all the colors the same way. But this semester, as it happens, most of you are looking at completely different stars. There's only one case here where two people looked at the same star. Okay. So hopefully this clears up a little bit what it was you've been clicking buttons on for the last week. And I totally understand that once you get into the weeds of that, it's really hard to keep straight. What was our motivation here? What are we supposed to be comparing? What did we measure? And so hopefully this video helps pull that all together for you. Do your best to come up with a draft set of slides. I will give you some prompt feedback on those Thursday. And I'm happy to meet with you anytime you want before we get together on Wednesday of next week to go through stuff with you, give you some, if you'd like some practice presenting it, I'm happy to do that with you. But my motivation for wanting the drafts in fairly soon is to be able to get you some quick feedback on things that you need to change. And to help make sure that you understand things well, so that when you give the presentation, you don't get tripped up by any questions. As with the rest of this class, the intent is for this to be a fairly friendly process and something you learn stuff from. It's not something where anybody's going to be asking you questions to try to trip you up or anything.